Our second paper, entitled Using the Hybrid Metal Extrusion and Bonding Process for Dissimilar Joining of Aluminum 6856 and S355.
I'm going to present this paper using the hybrid metal extrusion and bonding process for dissimilar joining of aluminum alloy 6882 T6 and structural steel 355. Outlines for this presentation is first motivation for this work, then I'm going to explain the HYB process, followed by the experimental part and the main results. So the motivation for this work is mainly 3 points, which is the maturity of the HYB process, the increased use of mixed material as aluminum and steel, and the challenges related to welding of aluminum and steel. The challenges related to aluminum and steel joining is mainly related to the large difference in physical and thermal properties, and the formation of brittle intermetallic compounds or phases along the bond line. These brittle intermetallic phases these phases, aluminum and steel, they are necessary to achieve bonding, but the high thermal input associated with conventional welding techniques leads to an excessive formation of these phases, which results in a brittle bond. And thus they determine the bond strength or the joint strength. So what we wanted to see was if the HYB process also could be used for joining of aluminum and steel. But before that, I'm going to explain to you how the HYB process works. The HYB process is a new solid-state joining technique which is mainly invented for aluminum alloys. It uses a filler material and plastic deformation to create joints at operational temperatures below 400 degrees. The current version of the extruder is the HYB pinpoint extruder, which you can see here. The extruder is built up around this rotating pin with an extrusion chamber, an extrusion head with open dies in the lower end, an abutment, and a stationary housing. So the filler material is fed from the outside of the extruder. And when this pin rotates, the frictional force between these 3 walls will drag the filler into the extruder, and this wall will keep the wire in place. So the wire will meet this abutment, and the pressure will build up in front of the abutment, and the material will plasticize and be continuously extruded through these open dies in the lower end. So in a real joining situation, the extruder head is clamped against the 2 plates to be joined, as you can see here. And they are separated from each other with a groove. Note that the steel side is machined to form a slope. This is to ensure that the pin is not in contact with the tool. No, the tool is not in contact with the steel. And on the aluminum side, the groove is the pin is slightly larger than the groove, and this is to ensure contact between the tool and the aluminum base material. So when the pin rotates, some of the aluminum base material will be dragged around with the motion and mixed with the filler material, which is extruded into the weld groove. So the filler material will flow from the upper region and down along the steel side, and some of the base material will be dragged from the aluminum side and mixed with each other. So the experiments we have done is transverse testing, like hardness measurements, tensile testing and microscopic analysis, including both optical microscopy and SEM. So here you can see the hardness results and an optical micrograph of the joint. And here you can clearly see the aluminum filler wire. This is the dark part. And the aluminum base material. And you can also see that the steel is not deformed at all. And here you can see the hardness measurement along this line. As you can see, this is the lowest part on the transition here. And the steel seems also to be unaffected by the heat in the process and reaches its hardness immediately. On the aluminum side, you have a point that is a bit larger than this point, but still quite low. And the aluminum base material hardness is reached after about 12 millimeters, which is the extension of the heat affected zone. So the tensile properties of this joint, it was found to be 150 megapascals, which is about 45% of the aluminum base material. But what was really interesting is the fracture path of these joints. As you can see, the fracture starts along the bond line, but it changes direction and continues through the aluminum filler material. Yeah, you can see it. And this means that sufficient bonding is obtained through most of these parts of the joints. Also, you can see that this is quite similar, or where we found the lowest point or lowest hardness in the previous slide. Also, we did some SEM examination. This was to see if there was any significant formation of intermetallics along the bond line. But at the highest magnification, which is 8000, we couldn't see anything. And this light area here, it's mainly believed to be an artificial effect due to the height difference of the aluminum steel when you polish it. Since the aluminum is softer, the steel will be a bit higher, which is this line. This is also quite interesting, as in conventional welding techniques, as friction stir welding and TIG welding, this intermetallic layer is possible to see. It's between 2 and 5 microns, and that means that in a standard SEM analysis it should be possible to detect this layer, because the lower limit that we can possibly detect is between, or it's 0.1 micron, which means that, yeah, if there is anything in this bond line, it's lower than that. Yeah, in fact, there has been an improved version of this joint, and another PhD student at NTNU has been able to detect this intermetallic layer. Her name is Tina Berg, and she made this STEM image, and she found the intermetallic layer, and it is of a thickness of 20 to 40 nanometers. This is also quite interesting, since if you have kind of a small layer, you need that to have a bonding. If the intermetallic layer is too thick, the brittleness of these faces will cause a brittle bond. And yeah, she's now working on seeing or figuring out which chemical composition these layers have. Also, there was done some tensile testing on this joint, and here you can see that even though you have a root crack between the aluminum and steel, the final fracture occurs in the heat-affected zone on the aluminum side, which is really interesting, I think, because the heat-affected zone in the aluminum it should be the weakest part in this case. Also, we found that there was a tensile strength of 273 megapascals, and this is about 73% of the aluminum-based material. So, the conclusion is that the successful joining has been conducted between aluminum alloy 6082 T6 and structural steel 355 using the HYB process, and there are no signs of intermetallic bases or oxides in a standard SEM analysis. And fracture occurs mainly in the aluminum and not along the bone line, which is also ensuring for further research on this topic and the use of the HYB process for dissimilar joining. So, yeah, that was it.
He gets 2 medals.